So now let's talk about mean shift clustering. So mean shift clustering is actually a little bit more advanced and versatile technique for clustering based segmentation. And here are two examples of the actual result of an algorithm of mean shift clustering. So this mean shift algorithm basically seeks local maxima density features in the feature space. So as you can see here, we have the image, and in this case we're not using the RGB value. We are using different color space. But if we represent this in a different color space, what it does is that it will actually try to find the peaks of these of these clusters and try to come up with an actual representation for it based on the different features. So now let's go into the actual explanation of how this is done. First, we have several set of points, for example, and then we define a particular search window, okay, and this is randomly defined, okay. Then for this particular window, we calculate the center of mass based on all the different elements that are within this particular search window. So once we find the center of mass, we calculate the mean shift vector, okay, and then we shift, okay, the actual center to the new center of mass. And then here we come up with now a new set of features that are within this search window. So again, we calculate again the center of mass and then the mean shift vector, and then we move to the next position. Okay, eventually it will actually come up with a better centroid that is represented as the local maxima for this particular cluster. Okay. So now all cluster in each cluster, all data points are in the attraction basin of a mode. So we talk about this attraction basin as the region for which all trajectories lead to the same mode. So as you can see here, we have different trajectories that lead to the same attraction basin, which is the center of mass of the whole cluster. So in this case, as you can see, we are not having a particular circle-based approach. So this is more of a following the different vectors that we are producing along the trajectories of the center of mass. Okay, so the actual algorithm can be summarized into the follow steps. First, we need to find the features. So whether it's that we define like either color or different gradients or textures, so we can use different features, and then we initialize the windows at individual feature points, and then we perform mean shift for each window until convergence. Okay, so once we have the convergence, then we merge these windows to end up in the actual local maxima, as you can see here. So for the image that it's on the bottom, we can see that initially from the initial feature space, we can come up with different representations of the clusters based on the actual local maxima that I found in each of the clusters, as you can see here. These are some of the results for mean shift. As you can see here, we have a more clear representation of the actual different clusters based on the color space scenario, and this is also quite useful for many other different applications. Here's another example. As you can see here, we have a clear partition of all the different segments of the image, and this is more applicable for example for labeling or for image labeling and learning. So there are some advantages and disadvantages of a mean shift algorithm. Advantages, for example, right now we don't have to assume that we have a spherical clusters, as I was mentioning before, and this is actually one of the main differences between K-means algorithms. So here we don't need to assume, the spherical clusters. And right now we just have one single parameter that we actually need to define, which is only the window size. But sometimes it doesn't. There's not too much difference between the window size. In some cases, it's also depending on the features, but basically this is only one parameter that we need to worry about. This algorithm also finds the variable number of modes, of basically of local maxima, and this is also useful if we want to come up with different ways of segmentation for the same image. Okay. And also here we have it's robust to outliers. So sometimes even though some outliers fall far from the actual cluster, they can also be included into the same cluster, because basically it actually depends on the trajectory of the vector. So if that particular outlier has the same trajectory, then it will be integrated into the same cluster. So some of the disadvantages, for example, is that the output depends on the window size. As we were mentioning, this is only one parameter, but still, it depends on the output size. So if we have a fixed window size, then we only have one particular result, which might not be the best result in all cases. Okay. Another disadvantage is that it's actually computationally expensive, because we need to perform the same operation many times and with many iterations for all the different data points. And also this algorithm does not scale well with the dimension of the feature space, because whenever we have more dimensions, then it becomes even more complex and it takes more time to compute. So let's talk about another segmentation method, which is binary based. So suppose, let's say we want to segment this image into foreground and background. So right now we want to know which is the background and the foreground. Okay. So once we have for example, like the background, then we can basically substitute the background into a different image, and then be able to compose new photographs. So this is also one of the applications. So let's just begin with the promise that we just want to segment this. So how do we do this? Okay, how do we actually perform this actual segmentation? Okay, as you can see here, in this case the foreground, it has the face of the llama has different colors. So if we perform just a color-based approach for this particular, it might be a little bit difficult. So now, one way is that we can give some help to the computer, and this help is as follows. For example, the user, we can sketch a few lines, a few strokes on the foreground and background, so the computer can know what do we mean with the foreground and what do we mean with the background. So it's just very few help. And then the question is, how do we classify the rest of the pixels? So in order to do this, we're going to be using a method that is called energy minimization, and we do this by first defining the label. As we already defined the label when we perform the strokes. Okay, so we also want to define this label, okay, to be able to classify each pixel either 0 or 1, depending if it's background or foreground. Okay, and basically we want to the problem consists of a minimization problem in which we have an equation that consists of the mass on the match cost, which represents how similar is each label pixel to the foreground or background. Okay, so basically we're gonna label each pixel and we're gonna try to find the similarity to the strokes that we already provide. And then this equation also consists of a smoothness cost based on the actual similarity of the neighbor pixels. And again, the output is that we can come up with a mask, in this case an image that is represented by 0 or 1 based on the different background or foreground. So for example, let's talk about the match cost. So in this case, we already provided some label, okay, and for each label we have each pixel has a particular label, and this label, okay, we can also, it consists basically of the sum of the pixels that have the distance for the particular pixel to the label. So in this case, we have that the distance from each pixel to the background, okay, it can be to the background or to the foreground, depending whether if it's either 0 or 1, okay. And we're gonna assign this whenever we have, for example, the distance it can be infinity when the label is not the same as the one that was already defined for the user, or it can be the other label if it's the one that the user defined already. So this is usually computed by creating a color model from the user label pixels, as I mentioned before. So let's look at an example right now. For example, we have this image in which there's an elephant, and then we provided some strokes. So for each of the strokes, we compute the model, and we can come up with the actual foreground or background. So in this case, this is the background, okay, if we define the red strokes as 0, okay. But if we change as foreground, then the change of the actual output image will be the opposite. So now let's take a look at the actual smooth cost. So this is based on the neighboring pixels. Basically, they should generally have the same labels, okay. Not all the time, but in most cases, when they correspond to the same object, they have very similar labels, okay. For example, if we have a particular image, then we can calculate this smooth cost, okay, based on the similarity of intensity of two particular points. So here the two particular points are P and Q, and we have a particular weight. So this weight is multiplied by the absolute value of the labels of the 2 points. So right now, for example, if we have 2 points that correspond to a particular region of the image, in this case, they correspond to the same color, then we have quite a high weight for the similarity of intensity, okay. But let's say we have another 2 points. So in this case, these 2 points fall into different regions of the image, and they have a different, let's say, different color. So the distance now, it's actually very, the weight is very, very small. So this is how we can actually define the smoothness of the pixel. So now let's talk about graph-based segmentation.